Right now, inside your body, there is a particle doing something your brain cannot process. It is moving through time backwards. Not metaphorically, not poetically. According to one of the smartest men who ever lived, mathematically backwards. And the strange part is, he did not stumble onto this by accident. Richard Feynman looked at the equations of quantum physics, looked at a piece of antimatter called a positron, and realized something that should not be possible. If you just flip the arrow of time in the math, an electron moving forward in time and a positron moving backward in time are literally, mathematically, the exact same object, same equation, same picture, same particle. Just read in reverse. So which one is it actually doing? Nobody knows. And by the end of this video, you are going to understand why some of the smartest physicists alive today think the answer might be both at the same time, and why that idea quietly breaks the way you think about cause and effect. Stick around, because there is a twist in the middle of this that even physics students do not get told until university, and it changes everything about how you see the world around you. Let us start with something you already believe. Even if nobody ever explained why you believe it, you believe time only goes one way. You have never seen a shattered glass jump back off the floor and reassemble itself. You have never watched smoke pour itself back into a chimney. You have never seen an old man get younger. Forward is forward. That is just how reality works, right? Here is the part that almost nobody tells you. If you look at the actual fundamental laws of physics, the equations that describe how particles move and interact, almost none of them care which direction time is flowing. Newton's laws of motion work exactly the same if you reverse time. Run the equations of the swinging pendulum backward, and you get a perfectly valid pendulum swinging backward. Nothing breaks. The math does not throw an error. Electromagnetism, the force that runs your phone, your brain, your heart, works the same way. Reverse time in the equations, and you still get valid electromagnetism. Even quantum mechanics, the weird rulebook that governs atoms, mostly does not care about the direction of time. So here is the actual question hiding underneath all of this. If the fundamental laws of physics do not prefer a direction, why does the universe around us so obviously have one? Why can you remember yesterday, but not tomorrow? Why does the egg break, but never unbreak? That is called the arrow of time problem, and it has confused physicists for over a century. But Feynman was not satisfied with just accepting it. He wanted to know what happens if you actually take the time symmetric math seriously, all the way, without flinching. And that is where antimatter walks into the story. In the 1940s, physicists were trying to describe what happens when particles like electrons interact using something called quantum field theory. It is brutally complicated. You have particles popping into existence, particles disappearing, particles influencing each other across space in ways that are almost impossible to track with normal equations. Feynman, being Feynman, did not try to brute force it. He invented a way to draw it instead. These are called Feynman diagrams, simple sketches with lines representing particles and points where they interact. A straight line for an electron, wavy lines for photons of light. And these diagrams became the standard tool physicists still use today to calculate what happens when particles collide. But here is where it gets strange. When Feynman was drawing electrons interacting with their antimatter twin, the positron, he noticed something. In his diagrams, he did not need a separate symbol for a positron moving forward through time. He could just draw a normal electron line and flip the arrow on it so it pointed backward in time instead of forward. That is it. Same line, same equation. Just reversed the little arrow. And the math for that reversed electron line perfectly matched the math for a positron. Not approximately, exactly. This idea has a name. It is called the Feynman-Stückelberg interpretation, named after Feynman and a Swiss physicist, Ernst Stückelberg, who noticed something similar around the same time. The interpretation says this: a positron is mathematically identical to an electron traveling backward through time. Let that actually land for a second, because most people hear this fact, and their brain just slides right past it without registering how insane it is. We are not talking about a metaphor here. We are talking about the actual calculation tool that physicists use right now, today, to predict the outcomes of particle collisions at facilities like CERN. And it works because, inside that math, backward-moving matter and forward-moving antimatter are two descriptions of the exact same thing. Now here is your pattern. Interrupt, because I want you to actually picture this instead of just hearing it. Imagine you are filming a video of an electron and a positron colliding and annihilating each other, turning into a burst of light. Now play that video backward. What do you see? You see a burst of light spontaneously turning into an electron and a positron flying apart. Strange, but okay. That is what time reversal usually looks like. Everything running in reverse. But here is the twist Feynman pointed out. You can also interpret that exact same backward video completely differently. Instead of thinking of it as light creating a pair of particles, you can think of it as a single electron that exists the entire time, just changing direction, forward in time as an electron. Then it hits a point in space-time and continues on, except now the math reads it as a positron heading backward through time to before the collision. Same event, same physics. Two totally different stories depending on which way you choose to read the timeline. That is not a coincidence. That is the entire foundation of how we calculate particle physics today. Okay, so if this backward time trick actually works in the equations, why does nobody experience time running backward? Why can you remember your childhood but you cannot remember next year? This is where we need to talk about something completely different from the fundamental laws, something called entropy. And this is the part that finally explains the difference between the math and your actual daily life. Entropy is basically a measure of disorder, or more precisely, how many different ways the particles in a system could be arranged and still look the same from the outside. Here is a real-life example you have felt 1,000 times. Take a brand new deck of cards, perfectly ordered, ace through king, 4 suits. Now shuffle it. There is only one way for it to be perfectly ordered, but there are more possible shuffled arrangements than there are atoms in the observable universe. So when you shuffle a deck, it moves toward disorder, not because the laws of physics demand it, but simply because disordered arrangements vastly outnumber ordered ones. It is a numbers game. This is exactly what happens with a broken egg. There is only one way for an egg to be a perfectly intact egg, but there are billions of ways for those same molecules to be scattered as broken shell and spilled yolk. So when the egg breaks, it is not violating any backward compatible law of physics. It is just statistically moving from an incredibly rare, ordered state toward one of the overwhelming number of disordered states. This is the arrow of time. It is not a fundamental law written into the universe's source code. It is a statistical tendency caused by the fact that the early universe started in an unbelievably ordered low-entropy state, and everything since then has been sliding toward disorder, like a ball rolling downhill. Your memories, your aging, the fact that you can pour cream into coffee but never separate it back out, all of that comes from entropy increasing, not from time itself having a built-in direction. Which means, on the tiny scale of individual particles, Feynman's backward-moving positron is not actually breaking any rule. It is simply working at a level so small that entropy has not entered the picture yet. Down there, forward and backward genuinely are just two versions of the same math. Now here is the mid-video twist, the part that turns this from a cool math trick into something that keeps physicists up at night. If backward causation is allowed at the tiny scale of individual particles, some physicists have asked a terrifying question. Could effects sometimes come before their causes, at least at the quantum level? This is not fringe science. There is a real peer-reviewed area of physics dealing with something called the delayed choice quantum eraser. An experiment where the choice you make about how to measure a particle appears, in some interpretations, to affect what that particle did earlier, before you even made the choice. Physicists argue fiercely about how to interpret this. Some say it is not actually retrocausal, that it just looks that way if you are not careful about correlations. Others take it more seriously and use exactly the kind of time-symmetric thinking Feynman pioneered to try to explain it. There is even a whole interpretation of quantum mechanics called the transactional interpretation, developed by physicist John Cramer, which builds directly on the Feynman idea, treating quantum events as a kind of handshake between a wave traveling forward in time and a wave traveling backward in time, meeting in the middle to create what we observe. It is one of the most fascinating, least talked about ideas in modern physics, precisely because it takes Feynman's backward positron trick and asks, what if this is not just useful math? What if it is telling us something true about how reality actually works underneath the surface? So here's the climax, the big reveal this entire video has been building to. Feynman did not just invent a clever shortcut for drawing particle diagrams. He revealed that the universe's fundamental equations are so deeply time-symmetric that an antimatter particle moving forward and an ordinary particle moving backward are, at the level of the math, indistinguishable. The only reason your entire lived experience insists that time only goes forward is entropy, a statistical avalanche set in motion by how absurdly ordered the universe happened to be at the very beginning. Zoom out far enough to the scale of a single particle, and that avalanche has not started yet. Down there, the future and the past are not separated by some cosmic one-way door. They are just two labels for the same line on a diagram, depending on which direction you decide to read it. Every single atom in your body is built from particles that, on paper, do not actually care which way time is flowing. You are, in a very real sense, a walking, breathing exception to the rule you have never once questioned. And that raises the question this video started with. If the universe's most basic building blocks do not experience time the way you do, what does that actually say about what time is? Not what it feels like, what it actually is. That is a rabbit hole for another day. If this cracked your brain open even a little bit, hit like right now. It genuinely helps this channel keep making videos like this one. Subscribe if you want more of Feynman's ideas explained the way he would have wanted them explained. Simply, honestly, and without dumbing down the parts that matter. And drop a comment telling me this. If a particle can move backward through time and nobody notices, what else might be happening around us that we are simply too big, too slow, and too entropic to see? I will read every single one. See you in the next video.